Dr. Sarath Kumar Maharana. We have Dr. Sarath Kumar Maharana, who I have heard a lot about from Dr. Kithis. And today I am also looking forward to listen to him speak. So let's start with a short introduction of Dr. Maharana. Dr. Maharana is currently working as Dean, Faculty of Engineering Technology, and Director in Charge, Training, Placement, and Career Services at MS Ramaya University of Applied Sciences, Bangalore. Now, he has earned his MTech and PhD in Aerospace Engineering from IIT Kharagpur, West Bengal. And in his more than 25 years of professional experience, he has served as the principal of Gandhi Institute for Technology, we call it GIFT. And he also was the chairman of the Board of Studies, Aeronautical Engineering and Aerospace Engineering at VTU, and was the head of the Department of Aeronautical Engineering at Acharya Institute of Technology, Bangalore. He was also a faculty of Mechanical Engineering Department at IGIT Odisha, what we call Indira Gandhi Institute of Technology. And he has worked at GE's facilities for aircraft engines and global research in Ohio and Albany, both in the United States, and Infosys Technology Limited in Toronto, Canada. He also held the position of Dean Academics at BPUT Odisha, which is known as Biju Patnaik University of Technology. And till now, he has supervised 20 MTech dissertations and 10 doctorate students. And from GE Aviation, he has a Six Sigma Green Belt qualification. He has published his works in 45 highly reputed journals. He also has served as speaker, editor for various conferences and journals. He has published many book chapters also, and I'm very honored to say this. His biography has been featured in the 2010 edition of Marquis Who is Who in America, and he has received both the Infosys and the GE Service Awards. And believe me, this is the shortest possible introduction I could make of sir. So we are truly honored to have you, sir. The screen is yours.
Okay. Thank you, Susri Madam and Kithis sir, for giving me this opportunity. I also welcome all our participants, our colleagues who are attending this session. Thank you so much for this. Time is 6 o'clock. All are tired after long hours of work. 1 second. Yeah. So before I proceed further, let me make very clear that my background is not electronics communication, so I will focus more on AI-enabled graphene and 2D functional materials for next generation semiconductors. So in between, I will be touching on semiconductor, their applications on the surface, but I will focus more on AI parts, the mathematics, the root, why it is happening, how the prediction happens, how a model works through Excel. I have got some Excel handwork we can also do together if you wish to do. So that will be more interesting than a normal presentation. But I have a presentation, very long presentation, but I will not cover all the slides though. Before I before I go a little further, let me give you a little information which you might have gotten by now in the last 4 days. Then why are we focusing on this semiconductor? What's big in this? And what's this functional material? What is the definition? What's the definition? And how AI is going to help? Why suddenly AI has come? Though last 50 years we have not spoken about it. Why suddenly AI has come? What could be the reason? We all are teachers. This is a faculty development program. So if we understand why part of it and how it happens, so then the other part will be much easier for us. Today, the global industry is at an inflection point. I request the participants to mute their mic for the benefit of others, so that we all can hear. Okay. All of us, after 50 years, our global industry at the inflection point. Most of us might be knowing about what is the inflection point mathematically. Let me give you a little more childish way of doing it. Inflection means when things are changing. And after that, there is nothing, then the downgrade starts, the inflection. Inflection is when the, mathematical, the second order derivative changes, the value is 0 and you get new curve, COP to cap. Okay, so that's basically called inflection point. That means something was happening and suddenly there is a change. Why that change? The change, who has brought the change? The AI has brought the change. In fact, I will tell you why AI has brought this change. Once upon a time, we were happy. The demand was okay. Semiconductor industry was doing pretty well. Then suddenly the generative AI came. We started using NVIDIA GPUs. We started using cloud. We started using semiconductor in a much bigger and better way. So when you have better things to enjoy in the technology, what you need power density, you need you need the very fast speed, you need better design, all that stuff. But if you look at this that way, we are actually not proceeding. Our semiconductor industry is not that capable enough to provide all these things immediately. So if you look at the Jensen, who is now the NVIDIA CEO, what he says is the energy is one of the elements of AI, and along with semiconductor. Even if you have semiconductor, if you don't have AI, then there is a problem. Now that we have a challenge, how to scale up this semiconductor industry by material design, by material design, manufacturing. So then we can actually think of how to do it at the grassroots level. So AI has come in to help. So what AI does here? AI is doing what it's supposed to do. It is just going to predict some of the interesting things. I'll tell you what are the things that it's going to do. It's an introduction part. I'll just take 2 to 3 minutes. If you look at this definition, frontiers in semiconductor and functional material. The semiconductor and functional materials, they are not the same. Fundamentally, they are different. Okay, so we'll discuss about that also. Now, in between, AI is inside that. So, for example, if I do not have AI, how this semiconductor industry is going to grow? If I don't have functional material, what will happen to my semiconductor? So these are very perplexing questions, and that also tells, okay, yeah, let's see what's going to happen. So then this artificial intelligence is nothing but a transformative enabler. What it does is, it is doing something which you are not seeing, I am not seeing. But the material that we are going to develop in the semiconductor industry is actually governed by the intelligence of the computer or the cyber system. Okay, what is happening inside is that which material, what is the percentage of functional materials are required in semiconductor? How can you decide what is the percentage of graphene? My topic will be on graphene. What is the percentage of graphene that you want to put in this original semiconductor material such that the conductivity is better, the speed is better, the scalability is better? So if you want to know all these things, we have to actually take the help of AI, because right now we do not have expensive experiment to do to find out this, and we don't have that much of time to wait, because there is a stiff competition in the market for production of these things. Okay, so if you go to the next slide, if you see the next slide, if you see here, these are all foundational.
Excuse me, sir. Sir, please full screen take कर दियो, sir. Hello. Hello. Yes, now it is.
Okay.
Yes, sir.
Yes. So let's see this. Yes. What has happened is, if you look at this manufacturing of semiconductors, starting from, I will not spend much time on semiconductor. I will spend much time on AI enablement. Okay. So, but before that, we must also understand how this manufacturing happen. What goes into making semiconductor? If you look at the processing, wafer, oxidation, this photography, etching, and all that, this is a general process here. And if you look at a particular semiconductor, you have three things: source, gate, and drain. So if you see, let's not go into detail of this, but all of us should know by now what's a semiconductor. If you see this drain, source, and gain, here is the catch. We have to actually design this part better such that there is no leakage, and it can scale up, it can compute, I would say compute lot of mathematical operations. It can also hold information much better than what it was doing 50 years ago. So all this complexity, complex engineering problem cannot be solved by human alone. So we definitely need something which will assist us in giving this knowledge to design, manufacture, and use these semiconductors. If I go to this very definitional thing, let's go to the definition of semiconductor. Since I am not from EC background, and you all from different backgrounds, you must appreciate one thing. What is a semiconductor? If you look at the semiconductor, it is basically a smart switch. I mean, if you look at the definition, very definition, the semiconductor is actually, it starts carrying the electricity only when it is heated. Sometimes there, that if there is no heat, that's very difficult to carry the charges. So the rate of charge, rate of movement of charge is like your electricity, right? Your current. So if you look at the definition, it's a smart switch, and this switch is available in mobile phones, computers, and solar panels, etc., etc. This is a clever switch. Then what is this? What are the examples? So there are some examples you can see here: silicon, gallium arsenide. You can just have a look at it. These are all available everywhere. So this is not a great thing. So if you see, these are all few examples. Okay. Now, similarly, what is the definition of a functional material? Now, between functional material and a semiconductor, there is a very thin difference. You look at the difference. Functional materials are the materials that do a special job. If you see the special job, here they do smart switch. It's a switch, but this does a job like a superhero. It can bend when electricity is applied. So it does the special thing. So functional materials are required. Graphene is actually a functional material. It is going to do a superhero job for semiconductor. If I combine graphene with the semiconductor, our AI, which we are talking about, AI, computation, GPUs, everywhere there is a butterfly effect. You will find that by smartly designing the functional material, and we can actually get a great future in semiconductor industry. So if you see, this is a special job done, and that is a smart switch. Now with this basic definition, you can just see, you can skip all this, it's not required. It is just a graphene oxide is one such functional material. And here you can see silicon is the semiconductor. But the theory, the concept will be similar in all the cases. Our focus is actually not on designing something new, but it is going to assist the material design. It is going to assist a much better semiconductor by doing certain thing. Now, if I want to change something, if I want to become a change agent, I must know what is actually happening right now. Then only I can change. If I do not know what is happening, how can I change it? So let us see how can we change all this stuff. So we will have a small exercise right now. The material behavior. If you look at this, this is a very, very sound, available formula everywhere. If you look at this exponential response, when it's a response, it's a conductivity, it is electricity, it is voltage, it is called just response. If you look at the response of the semiconductor or functional material, if you see here, there is an interesting correlation. This is an exponential storm sitting the right side of the equation. You can look at this. And this is actually the foundation of design of semiconductor. If you look at the design of semiconductor, functional material, everything starts from mathematics. And mathematics is actually the foundation for all design engineers. If you go to aerospace industry, you will find mathematics. If you go to process industry, you will find mathematics. If you go to electronics industry, there is a mathematics in it. So similarly, we need to understand what goes in the design of this. So if you look at the design, how the response happens. The response happens, if you look at this, some initial value which is kind of a constant for both the material. The exponential part is very, very interesting. If you see this exponential term, that actually does a great job for us. What is that job? I will show you through the Excel. there is a minus sign here, and there is a K here. K is a material dependent constant. Suppose this K is for semiconductor, it will behave differently. If K is for functional material, it will behave completely differently for the same temperature. That is why this response must be understood. This response must be understood. Yeah. Yes. Yeah, kindly mute Dr. Kshetrish. You can mute everybody except me. You can mute everybody. You can control this. Yeah, thank you. So if you look at this, semiconductor becomes more conductive with temperature, and then this parameter increases. But the magic is actually done by the K. K is nothing but a material constant, which we'll talk about it. Similarly, if you apply the same equation for a functional material, such as this, with the increase of temperature, this will be decreasing. So you will see this exercise first, and then we'll go a little further, then AI will come. But before we jump into the AI, let us see. I will now unshare and share the screen. One second. Yes, one second. Yes, hopefully it's visible. Yeah.
Yes, sir. Yes, sir.
It's visible.
Yes, sir. Visible.
Visible, no? Yeah. Okay. Okay, let us see this one. One second. Yeah, this is Excel. I will be sometimes zooming in, zooming out. Hopefully it's okay. Now it's okay. Yeah. Okay, now let us understand what is this. If I see, just now I showed you the a suitable material response. Response, as I said, no, response could be anything: a current, a voltage, a sensitivity. So this is a response. Now we'll see one interesting thing here. So this is what I have kept in front of you. Now what we'll do, we'll go here. So I have got some temperature. Don't worry about this temperature. This temperature can be changed. I will change the temperature. So I have plugged in this formula here, this exponential formula. I want to just show you the job of the alpha. If it is positive, what will happen? If it is negative, what happens to us? Okay, let's see. Okay, so this is temperature, and everything is constant here. Look at this. So I just gave, these are alpha values. Of course, K value I have used here K, but it's alpha material. For semiconductor, I'm using negative, and for functional material, I'm using positive because their properties are different. So it's a negative value, this is positive value. You just see the impact of K and the impact of this K, these two. And since I do not know the value, I just put 1 for this initial value. Now, if you see here, this formula is actually nicely integrated with 1 minute. Yeah, you all can see this is a very basic formula here. Now, what I'll do, you look at the semiconductor output. What I'll do, I will just change the value, just some number I will take. Not to worry, that's that same number I will take. You can see here, I'm just putting some number. Just a second. Well done. Now, so if you see here, yes, you see here, what has happened is the x-axis, you have got 0 to 100 temperature. This side, the responses are calculated here. Okay, so now what I'm just doing here is this. I want to just show you that we want to see the per same value, what is happening. If you see here, these values are anyway automatically getting calculated. You see here, these are exactly mirror image of each other. The functional material behavior and the semiconductor behavior for the rise of temperature, they are actually mirror image. Look at this. Now, if you have higher temperature, suppose you are giving higher temperature to a material. Now I've got 80 degrees. Look at this. What's happening? The response is increasing here, whereas it is decreasing here. And they are so much dependent on this K, which is actually in this case, this temperature sensitive coefficients, and they depend on the material and device development. So this K value, we can actually take another value just to see. So 1 minute. Because I've gone to I've zoomed it a little more. I'll keep like this so that you can all see. So now what I'll do, I will just take one more number. So I'm just putting some very high number just to give you a perspective of how things change. If you look at these numbers, look at these numbers and this number for the same. Only I change the negative sign, negative to positive. What exactly it said? What is the interpretation? The interpretation is that if you take a functional material, if you take a semiconductor, use the same response and increase the temperature here, you will find a different behavior. Now, if I put some functional material on semiconductor, okay, so what will happen is, these are all separately discussed. How the behavior will change. It is better to know how these two things behave when the temperature increases. Okay. Now here I have taken one example for current. Current is a response, for example. Now the current flows faster here in functional material, whereas in semiconductor it won't flow for higher degree of temperature. Because you can see your exponential term that T, the increase of T, this will decrease. This will definitely decrease. Okay, current will not flow at a higher temperature. Initially, you will see it will fall down and then it will be monotonous. Okay. Now I will take you to another behavior of the material, another interesting behavior. These are the things that we do in these materials first. Before we go to this manufacturing, let us see another interesting thing. If you see, this is a logistic saturation separation. What is this logistic thing? This is another law that we want to test. I'll show this test. Okay. Output from a semiconductor. This is the formula. Below you can see the formula. Let us look at this formula, logistic formula. This the machine learning algorithms also we use the same thing. If you look at this, this is a response. It could be current, it could be voltage, it could be conductance, sensor output, it could be anything, this side. And this is the maximum value of Y, this one. And there is an exponential term here. And these X values are inputs. These are, of course, these are all right side is input. Of course, you have initial value. You have got this X is changing. X, we have to fix it. In this case, T is the X value here. So T, and this is T naught. Okay. And the K is the material dependent. Now that I have got a functional material, I have got a semiconductor. I'm going to design something for the industry. Okay. So now I have to merge them. I have to put, something into this. I have to, this CVD I have to do, then dispersions, and then the package and send it to the market. But before I send them to the market, what I need to do is I need to study the behavior. So what actually happens here is, if you look at this formula, this is an interesting thing. There is inflection also here, you can see. Now for K, K is actually that value, this value, K, this K. I have taken positive and negative just to show a comparison. What happens if you can take this, you can also prepare similar one if you are doing some research. Yeah, you can put any number there. So not necessary. You just see one interesting behavior first, then you can play with this. If you look at this too, I have made this mirror image. Okay, now you will say, sir, no, I don't want to make mirror image. No problem, you can change it. Just to see what happens when the this is temperature, this is the response. This is temperature, this is the response. Here, with the increase of temperature, this is response is increasing and then decreasing. It will start decreasing. Now almost saturated. This is not decreasing, it is going to be saturated. If you see here, this is what is happening. Suddenly it starts dropping and then getting saturated. Actually, logistic is actually saturation. This is called saturation formula, in fact. This is the saturation. See what happens, even if you heat it up, nothing will happen. It will stay there. It will stay there. Now, so if I do little more exercise, if I do more exercise, bunny. If I keep this constant, to have a look at this interesting thing, both this you can actually join them, you can actually create one if you wish. Yeah, you can find out all this stuff if you wish to do data level, what is this, and all that stuff you can actually create. If you don't wish to prepare it, I have just kept it that the scatter plot, you can make it line plot, not a problem. So what actually happens here is, so why I'm showing this, this is by changing the sign convention of the material, the saturation also you can find out, okay, there is no point in hitting the material again and again because it already achieved saturation. What is the point of hitting it again? So current stops, everything stops here. Okay, so these values don't worry because these are all just experiment. These are all computed from this formula. This is computing. The central idea here is that we would like to see a saturation limit if you are hitting this semiconductor for some reason, if there is a temperature increasing in your clean room or wherever you are keeping your semiconductor, a time comes when this starts showing up. Okay, we will see another behavior of the material. Another behavior. If you see another behavior, this is RNS type behavior, this material behavior. So here what happens is, if you look at this, your activation, this is your universal gas constant, T temperature, and there are explanations are there here. You can see this explanation. 1 second. If you can see here, this activation energy, all these stops are here. So now these two materials, how they behave. Functional material versus semiconductor. This is interesting. You'll be wondering this. Look at these numbers. Look at these numbers. 10 to the power minus 12. Okay. Now for a small change, K value, you can play with this K value. You can modify this. I'll change the K values and see this. Yeah. So these values, if you don't like all these values, you can actually take, say, let's say, I'm just taking some other number. Yeah. So I can modify this number. Just I'll give you one quick demo. I'll just put file. Yes. Now, just a second. Some temperature which you like, 5 degrees each. Okay. Okay. So now you see, I have disturbed the whole thing now. I've disturbed the whole thing because you look at the temperature, I have disturbed the whole thing. There is no sequence because it's 35, 35, 35. So what I'll do, you can see here, everything is if you look at this, I've disturbed the full temperature because there is no meaning of this temperature. Now, if you give a little the older values, which was existing, if you look at these older values, if you come back, you can actually find out that these two are behaving differently. If you look at this, if you go to this plus side, I will show you one interesting thing. If you add a trend line, if you go to a trend line, you will find one. See, it's R square value. If I see this R square value, you know that how accurate the distribution is. I mean, if this is your regression line, this is the line that you are actually doing it. So this is not good. This is not good means if R square coming to 1 is a better number. If you look at this here, here we can actually see some trend line. You can see and find out what is happening here. Display on the R square value. You look at this. Look at this R square. This is an interesting thing. So this is actually capturing the physics part of it, the semiconductor. With the increase of temperature, this makes a lot of sense. Why? Because R square value has actually gone. Okay, R square value has gone. Has gone very close to 1, which means this regression line and the actual line that we are drawing is very close to each other. That means it makes physically correct, and that makes a lot of sense for the material. Whereas this 0.67, it's actually not good. It still has to improve. Okay, so now this exercise can be done to understand the material behavior, and not only that, the universal gas constant is already fixed. Temperature, we have to change because it has to be in Kelvin. Only factor that can be changed is activation energy. Activation energy, because this is an energy barrier. We all know that the band gap is this imagination. The lower half and the upper half. If the lower half have the electrons, upper half is no electron. So the electrons have to move, cross this band gap, go to the upper half. So this crossing is crossing this barrier, the energy barrier. That is actually the activation. That much energy you need to cross this energy gap, go to the level 2. Level 2 means upper half. So then the whole thing starts. That is the fundamental thing of the semiconductor, right? So that is why the temperature thing is coming again and again everywhere. In all the models that you are seeing, the temperature is coming, because without temperature, nothing will happen. Okay, so that is why these things we are discussing. Now I will take you to another behavior of this material. This type of behavior. Another behavior is little sensitive behavior. Okay, look at the sensitive behavior. This is y is equal to mx plus c. There is nothing great in this, but the slope plays a devil's role here. The slope, y is equal to mx plus c. That m is actually the slope. What is the job of the slope? If you look at the job of the slope, it's very interesting. If you see, same thing I'm doing for both. I'm increasing, I put both the materials in the same plot. Temperature is increasing, response we are observing. The green one, okay, 1 second. The green one, I will put in the, okay, legend I'll put, okay, legend also put. Now look at this legend, now you can see. You see the semiconductor, what is happening to the semiconductor and what is happening to the functional material. Which one is sensitive? You tell me which one is sensitive. Temperature is same, response is noted. One material sensitivity y is equal to mx. If I just 1 minute, I will do one thing. I will add one trend line here so that it will be easy also. And display one equation here. Yeah, display one equation here. I will also display one equation here. Display one equation. Yes. Now you can see how much is this. Okay, look at this. If you look at the both the graphs very closely, this color, the color which is green color, semiconductor, y is okay. I will take out this one a little bit down. Okay, and this one I will take up. Okay, now you see y is equal to mx plus c. Here the intercept is 5 because it's cutting here. Here the intercept is 0.5 because it's cutting here. Okay, forget about the intercept because they have started from there. Now look at the slope. Here the slope is minus. Here the slope is plus. Now why this sensitivityness has come? The materials are different. The behaviors are different. The proof, the equation that was developed long ago, probably a mathematician must not have seen this behavior, but now we are applying these models in the semiconductor industry, material industry. We're finding out the truth, which material will behave in what way. The AI will come next. If this foundation is clear, the AI will be very clear to us. If I cannot just use machine learning, deep learning, CNN, all that stuff back into my industry because I have not understood how this visualization of this material behavior is appreciated or not appreciated. Okay, if you look at this, these are all the central theme of this discussion. 1 second. Here, now we can also see slope. I can change. Now I will change the slope a little bit. 6 here. I will change the slope. So another 6. Okay, I will give the same 1 plus minus. Okay, now look at this. Completely different. They're crossing each other. One is completely falling down here. That is a functional material because it is now increase of temperature. It is fallen down. The response is it is almost dying. There is no response at all. At higher temperature, it is not responding. Whereas the semiconductor is responding so beautifully. Look at this, so beautifully, so beautifully. So now this exercise tells a lot of things when we work on the topic like this, because the materials is so important for us that we must actually appreciate the mathematics. Then AI will come right now. So these are all the behavior. AI will now take the data from this kind of study and predict that what exactly, how much graphene oxide you want to add in semiconductor to get a better response. How much will be the thickness of the semiconductor to get better conductance? How much the statistics will be known only when we understand them mathematically first, apply the data, train them, use the model, and then get this, and then it goes for manufacturing. The material should not be manufactured without understanding the mathematical behavior and the AI's comparison and validation before sending it for fabrication and to the marketing. So that's why this discussion is very important, that we all must teach that way, such that we all. Now I'm stopping that one. I will go back to my presentation now. 1 second. Just. Yes. So this is what I just now said. This is about this, and we saw the exercise. Now these are all covered now. Okay. Now this is also covered. Now next is, since our topic is after understanding the mathematical behavior, next comes, I want to improve myself. I want to do something better. I want to, see that the semiconductor industry, you said that the scaling up, the design will be better, power density should be better. So we want to make it better. But if graphene has a beautiful property, it's called wonder material of the world, a wonder material. It has got such a beautiful properties that will immediately take the credit for being the material of the world, and the semiconductor industry will see a sea change, a fabulous change, if the graphene oxide is added as a functional material to the semiconductor. What big change is going to happen, you can also see from here. See, for example, graphene, most of you might have seen graphene. You can also Google and find out the color, because in powder form or in liquid form. And only one drop is enough to tell the whole story about it. Graphene is that powerful. It has the good electrical conductivity. It has got the very strong yielding properties, everything. What is very strong material. I mean, we generate the composite material. We also put it to make the matrix very, very strong. Okay. Anyway, now coming to this semiconductor industry, let's see this. See, if I have to add as functional material to semiconductor, what will happen? See this 50%. I am adding the graphene oxide by volume, and before and after, you can see before adding the graphene, the K value was 0.012. After adding graphene oxide to semiconductor, I got K. These are all calculation again done based on this. I don't need to go back and forth. So these values are actually computed before and after adding graphene oxide. Okay. If you see here, there is significant change of the improvement of the material. Their conductivity has improved, their power density has improved, so materials properties have improved. So obviously, the industry will love to have an improved material, and they will buy from you, because I have got a better semiconductor. After adding graphene, my investment is less, so I will have a much better material for the manufacturing. So if you see, only this is an example. This is just an example. So which is this is commonly used in the industry. So this amount is enough to remain the filler enhanced regime. It increases everything that the semiconductor needs, everything that functional material needs. Here, the clear candidate in this case is the functional material, because the functional materials are essential for this industry as well. But if you see this 65% hike is itself is a pretty good sign that the graphene does really wonderful thing. If you little add this much percentage, only this much percentage, if you add more, probably you will not get what you are looking for, because graphene has its own limit to also jeopardize the properties, jeopardize the conductivity, jeopardize everything. So we carefully add the graphene oxide into this material, make sure that there is an optimum thing. Now, these are all from empirical relationship or industry is telling, and all that is telling. You will be wondering, sir, how do I optimize? How do I compute these values? Who can help me to compute and recommend to the industry that how much graphene oxide is required for semiconductor industry? A time will come. This is what is given by the industry. This is what, of course, we tested. But do you know if I add 0.6% graphene to semiconductor, do you know, can you tell me the result if I add 80%, 0.8%, what will happen to this? So such things will be known to you by AI. That's what is coming up next. So now, here is a catch that there are some examples. You can just quickly look at it. Say semiconductor is now, see, zinc oxide, silicon, conducting polymers. So if you add this geo into this, these are the things that changes. Charge mobility increases, decreases the activation energy. Why decreases activation energy? Why do you need activation energy? You need activation energy from to cross the band gap. Okay, so now if the activation energy is less, that is better only, because with less energy, I can actually push the electron from the bottom layer to the upper layer. So without even my energy saving itself is pretty good. So K increases here. Now, if you see the functional material 0.5% addition, what are the things that is going to do? There are some examples. So probably the titan oxide is there, vanadium oxide. There are some materials, new materials coming up in the market. But overall, if you see, K increases more strongly in this case. Here increasing, but here it is more strongly. So functional material and semiconductor materials are benefited by the addition of graphene oxide. The example which I showed is 0.5%, but you can try adding more and see the benefit, and a time will come, benefit may not come also. By more addition of graphene oxide may not give you that much. Okay, so these are all the explanations for the terminology, that these are the materials. I will skip this because, yeah. Now the question comes, what is that is lying in graphene oxide that is so interesting and it improves this material? Their materials are there for 50 years. Why? Graphene oxide development happened in 2010. A lot of papers have come out. 2010, there was someone, some scientist got a Nobel Prize for the wonder material. You can Google and see the 2010 only this has come. Now from 2010 onwards, so there has been a sea change. There is a tremendous transformation in the semiconductor industry. So what is that property of graphene that improves this material? Let's just have a look at it. Graphene does some interesting thing. What it does, you just have a look. If I add graphene oxide, it forms a continuous conductive semiconductive layer, basically, allowing the electrons and the ions to flow easily. So just now we said in a semiconductor, fundamentally that has the current has to flow, right? The jump of electrons. Now this enabler, now I will call it enabler, graphene, it adds that conductivity properties to the material. Thereby these materials become so powerful, and electronic coupling. So if you see this, these are the reason why it happens. If you want to go into details of this, we cannot actually cover the AI topic, but because I'm more interested to know why it is happening, what is actually more interesting to know before applying the AI concepts. So these are the reasons. Okay, next is the the prediction. Now AI is coming into that. So now that these are all happening, their imagination, that is all fine. Now we have got models, a lot of models we have. Now we have to predict. So if you can predict prior to manufacturing how beautiful it is, that the semiconductor that you are holding in your hand has got graphene oxide, has got a certain percentage of graphene oxide. Who is going to tell you? The neural network, the random forest, this boost, this 𝗕𝗫𝗃, there are a lot of AI models have come up now. Forget about this big deep learning things. Even simple machine learning models are going to tell the they're going to tell you this the amount of graphene oxide. You'll be wondering how they're going to do it. What is the mechanism? What is the mystery behind these deep learning models? How can they predict the amount of graphene oxide needed for semiconductor? How the neural network is going to tell me this? What is the beauty? What is the mystery behind it? All of us know that the neural network, I'm giving just an example of neural network. Most of you are working on different networks, machine learning algorithms. We all work. You are all working. I'm also working on few things. You may not be working on the domain that I work, but you will be definitely using it. But if you fundamentally see neural network, I will go to the next slide. You will see that how are they going to predict? That is a question to be discussed and understood also. So now if you see here, by addition of graphene oxide, how things have changed. Then after changing, then we collect the data. We have to train 80%, 70, 30, this division we do. Then the training is very important such that the prediction will be much better. Okay, so if you look at this, AI does many of the things, like it will predict, it will find out the K value, it will do this temperature, all that I don't need to tell. Yeah. So coming to neural network, we are talking about neural network. Neural network, I have this code. I can just show you 1 second. I'll show you one code here before we go there. See, okay, let me just stop here and then go back to my quickly to. We should know interesting thing that. Just a second, sir. Sharing my screen. 1 second. Yes, sorry. Yes. So you are seeing my screen, Ketan sir?
Yes,
Hello?
sir. Yes, sir.
Yeah.
Visible, sir.
Yeah, visible. MATLAB is visible here, there. Okay. Yes. Yeah. Just for the benefit of everybody, let me just tell something here. Since these codes are available, I was preparing for this presentation. I just want to bring to your notice. This is how interesting this. There are a lot of things here. Not to worry too much. I will go to one ANN. How this what exactly happens here? I mean, we all must know what's ANN and all that. One model, if you understand, it's we know the theory, all of us. There is just linear equations and all that. But what exactly happens in this scenario is this: we go to 1 second. We go to this. Yeah, this is semiconductor plus Joe. Okay, this 1 second. There are some codes here. The basins. Here I can show this. Yeah, directly I can show here. Yes. What is happening is, yeah, because since you don't know the values, we have to give some values and all that that you leave. But the crux of the problem is that in artificial neural network, what we do is we have to give the neurons, right? We have to give the neurons. They will predict. I cannot see here that a lot of codes are there now. So okay, not to worry, no worry. So what exactly happens is that, that in the artificial neural network, yes, we have got something to predict. Okay, so let me go to the theory part. 1 minute. I'll come back here quickly. Just a second. Here we have. Just a second. We have some formula here. I can directly go there. Wait, I'll go to this basic formula first before we. I think it's lost somewhere. Here, yes. Yeah, you just look at this slide. That's an interesting thing. If you want to compute the neural network, okay, let's say I'm using neural network to predict the geo part of it. Suppose this is a geo part of it, and they are called the weights. WEITZIGHT. Weight. Weight means importance. That's it. Weight means importance. I have got A, B, C are the inputs that I collect. These are the inputs, and these are called the weights. These weights, if you look at in a neural network method in machine learning or in normal textbook also, you will find two interesting things. It's a linear equation, but our real life is not linear. It is non-linear, right? So what happens is that this is uncertainty. That epsilon you can see here. This is uncertainty because this has to be there. What it says is any linear program, any ANN or anything that you see, CNN, ANN, or machine learning algorithm, fundamentally they're linear equation. Fundamentally, because computers cannot process the non-linear things. That's why we just do linearity, then convert this into the models. Then we have got activation function and all that. Forget about it. What actually happens here is that we are talking about graphene oxide. What will be the percentage of graphene oxide that has to be added to semiconductor? That is the question. And the answer should be weight. Suppose to graphene oxide, this A, B, C are the three inputs. Graphene, I will give the mechanical behavior, one value, mechanical behavior. I will give its compressibility, conductivity. These are the properties which cannot be changed. Okay. Now, this is W1, W2, W3 are the amount. The amount means which is a variable, because weights are always changing. Why weights are changing? Because initially we'll guess some weights. Okay, let's put some value and give some importance. Then calculation happens. Then you will find some number. You will not be happy with the number. What we do, if you are not happy with the number, here is one. If you are not happy with the number, here, I think, yes, here also I can show you. Yeah, if you are not happy with the number, these are called actual importance. If you are not happy with the number, you come back, take the difference between the one that you have computed and the one that you started with. You started with some number and you are computing one number. So you take the difference. Take the difference, square it. Why you square it? Because if you square it, you will find out the error, more error, because you will find how big is the error. That is why we square it. You square it, then you say, oh, I am not happy with this error. Then again, the W value changes. The W value changes, the error also changes. A time comes when it converges. That's the beauty of this ANN actually, because it is not an ANN session. Otherwise, I would have told you a little more better. So fundamentally, what happens is like all these equations that you are seeing everywhere, these are all beta, these are all nothing but the importance, whatever you will see, these are all the importance, yeah. So here, what has happened is, coming back to this, here in this case, we are trying to find out the band gap. That's why this exercise is given, but fundamentally, the equation is same. Everywhere you will find one weight and one input value, x1, x2, x3. If it is W1, x1, W2, x2, W3, x3, and this is uncertainty. Gradually, we want to reduce this epsilon, this one, and this W1, W2, W3 are going to change. Why they are changing? They are changing depending on smartly they will change. Smartly, you don't need to do anything. They will be just going, changing in the algorithm, and the new values will be automatically getting generated to find a value of EG in this case, or the value of GO, which you are actually expecting. So that's why this beautiful thing happened here. Now I will go to our where we started with. 1 second. Just a second. So if you see here, if you see this graph, that is what has happened here. AI is predicting some red line. You can see the red line is predicted by AI, and the blue dots are actually the actual semiconductor values. I mean, the geo values. What it's saying is the fitment. Here it is fitting little bit better, but here it is okay. And functional material and semiconductor, this is a difference. Actually, you can see. Here is one, with and without AI in conductor. See, if this is without and with. So what it's saying is semiconductor, this is semiconductor AI. This AI is predicting, looks similar, exactly similar. Same temperature, you can see, same temperature. You're also predicting same behavior. This is a video, I guess. It has to play. You can see this video. You can see here, by increasing, you can see here, by increasing this geo value, what is happening to this conductivity? This is a response, semiconductor plus geo, functional plus geo. So that's why this is one. Here, if you see here, these are two different materials. Geo part is added, semiconductor is behaving this way, functional material is behaving this way. You can see here, one more time, slowly I'm moving. You can see here, temperature. This is awesome. Actually, I like this part because it actually connects us ANN versus actual, because you can see these blue lines are embedded inside ANN. So that's why you cannot see though, but it makes a lot of sense to study and understand the behavior of artificial neural network and how this is going to take the behavior. What it says is that your geo addition is going to improve the property. Okay, so how much improvement? And you can see this next one. There is another one. Here is another one. So yeah, so what it says is there are four things here. What are the four things? Semiconductor, physics based semiconductor. This is physics informed ANN. That's functional material physics, functional material fine. So if you see, looks like, okay, this case is very ideal. That's why it is all matching very well. But geo addition is also contributing equally. Looks like it is equal, but it's actually not equal. When you zoom in, you can find out. From the surface, you will find it looks like equal, but there is difference, in fact. Now, go back to this. This is a basic slide which you will tell, like there are two levels, P, N, and all that. This is the basic level. I was talking about this activation energy is required here only to cross the boundary, right? So this is a fundamental thing. And now, if you see, we have graphene and semiconductor. This picture tells a story. If there is no AI, let's say there is no AI, what will happen? There is no AI and I don't need graphics. Both are not there. Imagine the situation that both are not added at all. What will happen to our industry? Our industry will be like this only, no? Semiconductor structure. Now, many things are not happening because I need a regenerative AI, ChatGPT, for example. See, ChatGPT creates a lot of images for everybody, millions of users. But ChatGPT is computed in some hardware, right? That hardware has silicon, and hardware has a silicon. The silicon is designed by whom? If the silicon which was used in 1960s, can you use in the server which is used in 2025 for generative AI? Or for, in this case, you have got a lot of transformer today. They compute the cloud computing, or you can edge computing, whatever computing you have. All this computation happens in a material like this one, materials. So now, so these two are glorifying their life. They are improving their values by adding a lot of new stuff. This guy is predicting through your intelligence, and this guy is adding values. Now, to help this guy, AI computation, this guy is like a fish. You are using the fish oil in the fish, basically, to fry it. Basically, AI needs semiconductor, and semiconductor need AI. It is like that way. Okay. So if everything is running fine, then what is the issue? What is the issue now? The issue is mainly silicon design and manufacturing. So once the AI predicts better and the manufacturing will be better. Okay. So this we can actually leave. Yes. Yeah, I just mentioned to you that this we can skip. Okay. These metals are definitional. We can skip this. Okay. Now, this is another thing, of course, I have shown you. Effect of graphene on semiconductor. I think that also I showed you that what exactly happens, how this band gap is improving by addition of semiconductor. Band gap, you can see that red ones and the green ones, blue ones, that there is a significant improvement when the geo is added. The geo is added. And then next comes this. This is an important slide. We all need to know few graphs, few exercise you saw. Then the AI, how AI is going to enable the material discovery and property prediction. Okay, the models, a lot of models, I told you this. Now I showed you these models such as and sensitive models. ANN, I just now I told you. We have got many models, regression model, which is the simplest one, regression KNN, ANN, then support vector. There are many models available in the market today. Artificial neural network, recurrent neural network, LSTM. There are many models available to do what? To do the prediction. Fundamentally, they're going to do prediction. Okay, how someone predicts, that matters, that goes to that algorithm, that goes to the algorithm part of it. The algorithm for ANN is not same as regression. Regression is simple, y is equal to mx plus c. But in ANN, you find something else. So whatever may be the algorithm, the job of all these machine learning models, predict something which you desire for, predict something which you want, predict something which you are waiting for. Okay, so that is why the material discovery and property prediction has been very easy and productive because of the evolution of AI, and that has actually changed the paradigm of this industry. Then process optimization, the process which was followed long ago, 50 years ago. So I was just reading the literature where I found very interesting thing. Murray's law says that when the demand increases, you will be surprised. When the demand increases, the cost should come down. But today, reverse has happened. The demand is increasing, the cost is also increasing. If you look at this hardware cost of GPU, the NVIDIA is selling, it's going like a bump cell, like it's going like in CR. Why? The demand is increasing. Why the cost is not falling down? So Murray's law is now challenged because of this. It's an economic law that says that the demand goes up, means this price should come down. The price is going up as well. So this has come after 50 years of research, that now it is the time that the AI should come to help all of us, all engineers, to change the whole scenario. The cost should come down if the technology is better. Now, process optimization, material discovery, device, and design. Now, before I go to the next slide, I will tell you one thing. Most of you, if you have the background in computational fluid dynamics and EC, one common thing I found during my research and study is that here also there is a continuity equation. There is an electron continuity. In fluid mechanics, you will find a continuity equation. Here is a charge conservation or current charge conservation. There it is your conservation of mass. Okay, so if you see this basics of Newton's law in your in our mechanics, here there is a quantum mechanics. Without quantum mechanics understanding, the silicon's physics cannot be understood. So the quantum mechanics, the classical quantum mechanics, is the beginning of the silicon industry. Okay, later on, the quantum mechanics became the foundation. That is called your physics part of it. Then came your 𝗕𝗏, technology, computer and design, where we see the design with continuity, analysis, and manufacturing. It's a similar. You will find a lot of similarity in the thought process of this product as well. Okay, so if I put together all that stuff, so you need physics for device design. You need few laws like your Schrödinger's law and your lot of laws you have that package it so well that design of semiconductor is completely different ballgame. Once you design, you hand over the device to the engineer who do the simulation part of it. Who do the simulation, they understand both physics side of it, Then after the simulation is completely done, validated, they give it to the fabricators. Then only the whole thing completes. Here, yeah, these are all foundational. We just see first generation silicon, second generation silicon. I think we can skip this, what was the situation. And yes, here this graph is another interesting thing that we can see. Just now I said that AI across semiconductor workflow, from material discovery, because material discovery comes from the behavioral understanding. If the behavior is not understood, what are you going to discover? Okay, then process optimization, the coating, the process, the CVD, and the device design. For the entire process, AI is just here. Between material discovery and process optimization, you have got AI. Okay, then this I discussed with you. Yeah, this we can skip. These are all foundational thing. I think I mentioned to you all. Yes. This is, again, we have repeated. If you look at this, these are all very foundational mathematical relation, which is used in the regression model, is AI model, of course. If you look at this, left side you have got Y, which is going to be determined. This is what you are going. This is called response. Right side, these are called predictors. They are called predictors. You have got a lot of predictors here. Actually, S is a predictor, L is a predictor, C is a predictor, and epsilon is actually the uncertainty that you don't know. A0, A1, A2, A3, these are all the coefficients. Okay, if you look at this, they are the coefficients, regression coefficients. They are also going to change. Okay, now they are very sensitive to your this thing. They scale up and scale down these values. If you, why the what the product is doing, why they are multiplied. The multiplication, the job of the A1, A2, and all that, they are all the scaling up, scaling down, nothing else, nothing else. So that is the job of this, because they are nothing but you're like your weight now. We just now saw weight of that particular predictor. That's why they are there. So you compute one value, EG value, subtract from this, do squaring. The squaring is done to find out the error value. Square is done only for that, because negative value becomes positive, positive becomes positive by squaring, right? That's why you want to know, okay, this much error has come. The predicted value, the actual value, if you subtract, that becomes delta, right? So delta, if you square it, this becomes a number. And if it is a large, you reduce it. If it is okay, then you converge it. So here is the output of that actual prediction. You can see here, yeah, prediction. Here, actual band gap. This is actual. This is predicted. Looks like this is very similar. I mean, this red line is nothing but your ideal XY plot regression one. And this is predicted well for this. And I think, yeah, this may not play. Okay, I'll leave it. Yeah, this is just wanted to see how this slope variation is there. Okay. And similarly, any mathematical model you see, one interesting thing, you see a product like this, a summation sign. These are actually the importance parameter or the weights type. This is a pure linear equation. And the right side is very important for us, because the X value is the predicted, as I said just now. So if this side is very good, you find out EG, and EG, I showed you one calculation as well. So in MATLAB or in Python, your SI, you can do all this stuff. This is again polynomial, you can skip it. This is one electron microscope imaging, say let's say semiconductor. So what has happened is, this is synthetic. Actually, it is not actually available with me, but I just generated it in Python. This is a scanning electron microscope for a semiconductor. What has happened is, there is a defect here. So AI is predicting this defect. You can see here. There was a defect here. It created an image. And here you can see it is highlighting, oh, you have got a defect. So this kind of very small, minute thing that you cannot see, you can only see in electron microscope, that kind of ability of identification is with AI. So that if you suppose, for example, it goes for manufacturing, how devastating will be the computation. Imagine the computer will not, the computation, CPU or GPU, TPU, wherever you are applying, this will not be computed at all, right? So this is there. Chemical vapor deposition with CVD, I told you many times. So this I can skip because we cannot cover everything. So I've just highlighted that AI in process optimization. Yeah, this is this is for manufacturing. If you look at this, how the AI, artificial intelligence, adjusts how much temperature, what is the gas flow? If your gas flow is here, because when you manufacture the semiconductor, we need to do this vapor deposition. The vapor deposition is actually nothing but the gas flow. And these three components are interesting thing to note, that this equation has to be AI based. Like I must find out how much is Q. So that computation happens using this model. Each part is explained. Okay, this is actually this is called inflection. All of you can see here is going up and inflection. So after increasing the temperature, it is actually falling down. Film quality is not improving. Once upon a time, it was improving. After 200 degrees Celsius, it is falling down. It's inflection only. Okay, so this is all AI predictions. So why this happens in real coating and all that you can skip. Thin filming is okay. This I don't want to consider now. We don't have time. I think we have got 5 minutes to go. So you can skip this. Here I can tell some interesting thing. I have done some hyperlinking. Most of you may be interested to know later on. I'm pretty sure that you will like it. Bayesian optimization is one which we are doing in silicon industry. Why? This optimization, I found one of the finest optimizations. We have got many optimization in the past. Most of you, if you are using MATLAB or anything that you are using, you have got so many optimization. This is particularly interesting because this one is based on the recently acquired information that comes. It optimizes. It is so dynamic. You optimize, but generally when you do optimization, we do have constraints, a lot of constraints, objective function, you optimize it. But this guy is a little different. This guy depends upon the data that comes in, then the optimization begins. So it is so interesting. The semiconductor industry gets benefit out of this Bayesian optimization because it works on the facts and figures, I would say. Facts and figures, not on the thing that is already once done means done. No, it works on the data that comes in. That's why this optimization is normal optimization only. But the data that comes to us is latest, and based on this, it is optimization. And the process of Bayesian optimization is actually accelerated by a surrogate model. Surrogate model is why we go for surrogacy. Surrogacy is the no pen. There is a proof for this. Surrogacy that is a surrogacy. That is the same model we also use here. You have a model, AI model. It will just predict the value. It will give input to the Bayesian. Bayesian will predict optimization very fast. That's why it takes the help of a surrogate model, and it computes that value. That value becomes the blue-eyed boy for the Bayesian model. That's why it becomes very smart and easy. That's why silicon industry gets a lot of benefit out of this. And that's why there is a connection between this prediction and uncertainty. They become very fast. You can see here this Bayesian, how it works. It continuously takes the input and modifies this. This is generated in MATLAB 2024. This is very recent one. I was just trying something. So Bayesian, how it will. You can see here this blue line. No, this blue line. See, this blue line is become straight. You look at this blue line. Follow this. There are two things working here. One is this surrogate model, and the other one is Bayesian. Both are actually in job to get things done. That's why it's so beautiful, and it makes a lot of sense for the silicon industry to predict. And the AI predicts this. These are the AI predicted IV current versus voltage currents that you can skip all this. This can be skipped. AI can actually do the reliability and aging of the semiconductor. So this is the thing. This is the basic equation. The data set that we use for all computations purpose is actually generated by myself, because there was no data available to me. So I had to compute using this formula. So that's why I mentioned that. Then LSTM, short-term memory. Basically, these are all algorithms. What they do is they take the historical data. I mean, what is happening behind me, that data also comes here, LSTM. That's why it's more powerful, like your RNN. RNN will recurrent neural network, but this guy is a little smarter. This guy will take the latest data, which is just happening behind. That's why the semiconductor gets better benefit for the addition. And this is material property. You can see this AI, it predicts the degradation. When the semiconductor is going to degrade also, that I can know. That's an interesting thing. Okay, some of the observations I can skip. And this, we are almost close. Yeah, that we can see. Yes, thank you. Thank you. I think I finished before 5 minutes. Yes, over to you. Any question? You all are there?
Yes, sir. Yes, sir.
Okay.
Yes, sir. We are all here.
Yes.
So please, dear participants, please ask any questions if you have.
More than question, did you like it or not? That is important. Questions anyway to come. You can write to me later on if you are busy elsewhere. No issues. But overall, hopefully, I just covered few things. It's a vast topic. So yeah, sorry for that. There may be some other better way of presenting it, but I tried my best. Yeah.
Oh, sir, it was wonderful, sir.
Very knowledgeable,
Hello?
sir.
Okay.
Excuse me, sir.
Hello.
Good evening.
Yeah,
Good
anybody
evening,
wants to
sir.
speak? Yes, please.
Sir, is there any difference between PIN means physics informed neural network and the application of artificial intelligence?
There is in physics informed neural network, we use the physical laws. In normal artificial intelligence ANN, no, we don't use. Simply we take the data set without even understanding the physics. If you write the two codes, there will be physical laws will be there. That's why there is a big difference. Not there is a big difference because you have to satisfy the physical laws and the neurons capability, right? But in normal, yeah. So thanks.
Okay, sir. Thank you, sir.
Any other questions, please?
Hello, excuse me, sir.
Yes,
Sir,
please.
myself is Bhagya. Sir, the session was knowledgeable. It's a very nice session, sir. Sir, I have a doubt, sir. In the neuromorphic computing, we use matrix vector multiplication. Which algorithm is suitable, sir?
Come again.
Sir, in neuromorphic computing algorithms, CNN is there, RNN is there. Which is most suitable algorithm, sir, to implement matrix vector multiplication?
Yeah, you have image there. You have image, no?
Not image, sir. Just
no image. See, CNN is used for imaging only.
Yes,
CNN.
sir. Yes, sir.
Yes. So if there is no
So
normal,
if in case in the neuromorphic computing system, if you use the memristor,
then normal ANN will work. Absolutely no issues.
ANN.
ANN. Yes. If only see, we go for CNN only when there is image.
Fine, sir. Fine, sir. Fine, sir. Thank you so much, sir. Thank you, sir.
Sir, Monica is asking from where we can get data set.
Oh, very interesting question. Okay. I think I mentioned here. I have you see data sets, databases. These are the places. 2D Metpedia, Materials Project, Flow. These are the places where you can get. Okay. Or suppose you have a lot of difficulty, you can generate your data. That's data set also. These are the places you can see data sets. And there is one second. Actually, what I have done, because my time was also precious for me, so we can some data I took from there and some I generated like using this. Okay, so you can generate your own data, synthetic data also. You can use if you know the this is general one which you can see here. Current voltage you can predict. You can give the time range from 0 to let's say some time. It will generate a lot of information, 1,000 samples, whatever you like. You can generate. Yeah, this much I know. Others may be knowing better than me, but this much I know.
Any other questions, please?
Sir, I have a question, sir. While you are explaining about that Excel sheet regarding the data to put the graphs, all those things for explaining the change in parameters. So those things for explanation, do you have taken that in Excel sheet or we can able to integrate through any other programming language?
Oh, okay. Yeah, I like the the traditional way of doing it, so that's why I've used Excel. However, you can use a Python code for this.
Okay, sir.
You can use just if you write this. If you have this normal matplotlib or MATLAB, see, most of the time I've used MATLAB for my
Okay.
presentation, but some of the things I have actually with me, I have also used one second. Some of the things I've used. 1 minute. Will not show anything. I'll just tell you that. Some NumPy. There are a lot of things I have used, in fact, here. Yeah, so you can use this PyCharm. I am using PyCharm, of course, to generate some of the things. Yes.
Okay. Thank you.
Okay, anybody having any more questions? Dear participant, having more questions? Otherwise, we will wind up. Okay, sir. Sir, thank you very much. You have considered us, and you are given your time from your busy schedule. We are very much grateful to you from our coordinator and co-coordinator and from our organizing team also. And I am very much thankful from entire REC fraternity, sir. I'm very much thankful. And your today's presentation was mind-blowing, sir. And depth, we went so depth that we are interesting. Where will be the conclusion? Where will be the conclusion? We are waiting. We are waiting, and we got a lot of knowledge, sir. Lot of knowledge, sir. Thank you very much, sir. And second, sir, thank you. If
Thank you so much, sir.
you can say.
Thank you so much, sir. Thank you so much for your time. Sir, we're truly honored to have you, sir.
Thank you. Thank you. I must thank all the participants. I know that time is 7:30 here, and some of you are busy in the daytime, and now I'm not sure how much I have given to you, but hopefully you like it and you start using in your classroom. Your students will love it. I'm pretty sure.
Yes, sir.
Yeah. Thank you.
Okay.
Thank you.
Okay.
Sir.
Yeah. Namaste.
Sir, namaste. 𝗕𝗫𝗓 here.
𝗕𝗫𝗓 sir. Oh, acha, okay. Yes, sir. Very nice, sir. Okay. Aradhya sir, you are there?
Yes, sir.
Oh, you are at it? Oh, yes, nice. Oh, I didn't know that you are there. Oh, very wonderful. Wonderful.
Yes, sir. Next presentation in mind, sir.
Huh?
Sir, namaste, sir.
Next presentation in mind.
Okay. Yes. Oh, yes, yes. Okay. Thank you. I'll come out then. Thank you so much. And continue, sir. Thank you. Okay. Yeah.
Ma'am, please start the second.
Yes, sir. Yes, sir. So for session 7 we have MS 𝗕𝗫𝗓 𝗙𝗵𝘂 sir. So for a short introduction, he is currently serving as the CEO of Silicon Microsystems. He has 33 years of expertise in VLSI, embedded systems, automation, and robotics, and has worked in various industries. And as a mentor for government initiatives like Elevate 100 and FKCCI's Manthan, he has helped startups turn ideas into impactful venture. As a proud Rotarian, he has led projects that earned 5 Guinness World Records and established vocational training centers to uplift communities. He has been recognized with the Rotary Vocational Excellence Award. He has been awarded with numerous honors and awards, namely Rotary International Vocational Excellence and Leadership Award, holder of 5 Guinness World Records and community service projects, honored as Idea Man from Innovation, Incubation, and Entrepreneurship Ecosystem of Educational Institutions. He is involved in various government funding projects like Impact, TechIP 123, VGST, DST, AICT, UGC, AIM, RUSA, 𝗕𝗵𝘂, etc. So thank you so much, sir, for joining us. We are truly grateful to have you, sir. Sir, the screen is yours.
Thank you very much, ma'am, giving an opportunity to have a presentation of mine actually to your faculties. Hope I'm audible.
Yes, sir.
Okay. So yeah, actually, just this is mine is the last presentation. By 9 o'clock it will end.
Sir,
Will it end by 9
sir,
o'clock?
couldn't hear.
Will it
Sir,
end by 9
sir,
o'clock?
sir, it's audible, sir.
No, is it this presentation will end at 9 o'clock? The session will end at 9
Yes,
o'clock?
yes, sir. Yes, sir. 9 o'clock.
Yes, sir.
Yes,
9
yes.
o'clock. Yes, sir.
Okay, that's the last session.
Okay.
Is it that last session?
Yes, yes, sir.
Sir, today's
Okay.
last
For
session,
today's
sir.
last session it is.
Okay. Yeah. Okay. And audience is more of faculties?
Yes, sir. All our faculties, sir. Faculties.
All our
Okay, great.
faculties.
Yeah. Okay. Thank you very much, respected dignitaries and faculty members. And most of the time, actually, it's on the semiconductor devices and as well as design technologies. So the faculties are involved in these two categories, will be more interested in understanding the new concept and technology, which is, I think, which is my topic, the latest trends and technology in semiconductor industries. And see, we are talking about semiconductor industry. Can I share my slide?
Yes, yes, sir.
Is it visible now?
Yes, sir. Yes, sir. Visible, sir.
Okay. Okay, when we're talking about emerging technologies, usually in innovations of semiconductor, most of the time actually it is we talk about transistors. But now, from simple transistor, it is getting revolved on actually more on integrated systems, designing for specific applications. Correct? So it is not that only the transistor, it more on different parameters. Okay, it is just we'll check out actually what are the other parameters we'll also reflect on while designing, and also what are the different things are coming up in the industries on the technology based. One is actually for more than half a century, the semiconductor industry privileged simple, like on power of ideas, the powerful ideas, smaller transistor lead to better performance. That's correct, right? So Moore's law defined the generation of computing, communication, and consumer electronics. But today we are talking about critical transition point. The industry is no longer driven purely on the transistor scaling, but it is on the application driven. So that's nothing but actually system level innovations. Okay, so but also we are also talking about whatever the innovation is coming up. So innovations are more on digital economy and national security and energy and mobility. So if you talk about digital economy, everything, many things, it's happening on the digital economy, powering cloud computing, data entry centers, and digital infrastructure, everything. Okay, and while doing that, actually, we have to take care of our security also, like defense systems and as well as security on the communication and strategic independence. It is not only the national security, it is also on the digital economy security also to be taken care. Okay, energy and mobility. While see now we are talking about electrical vehicles, renewable energy system, and smart grids. So that is one more segment. It has to be taken care. Semiconductors have transformed from enablers to strategic assets, forming the backbone of the modern technological infrastructure. That's how actually it is. So total semiconductor industry it is evolving. See, even while starting with one design aspect, like is it we are designing a mobile or is it we are designing automobile? So when we take both the categories extremes, right? One is the smallest and one is the biggest. So for both the applications, we need electronics is important. Electronics makes a lot of difference. While doing that, any of the designs, we are talking about safety, cost sensitivity, performance, reliability, time to market, and unit cost. If you see the automobile, then it is more of safety taken care and performance, reliability, and time to market, and cost is all or everything is high. But if you see the mobile, it is more of like on the they're already standardized on the safety and performance and reliability. And time to market, every 2 months, 3 months, technology is evolving. So as like we have a less time actually to do the marketing. Okay, when you talk about the unit cost, it has to be as much as low as possible in the mobile, as much as high in the automobile sector. That's how actually the differentiations. And of course, the industry revolution also we have seen like 1 to 2 to 3, 4, and 5 industry. While doing that, now next future of industry 5.0 is going to be a human-robot collaboration, customization, and cognitive systems. From it's almost it is changing the world from your cyber physical system to IoT and network communication to the human and robot collaboration. And if you see that global semiconductor market, yes, now and if you see that by another 5 years, it is almost 700 billion to 1 trillion. 1 trillion is the semiconductor we are talking about, but 10 trillion is application based. So we are talking about CAGR almost is about 6 to 9% growth. And if you see that where are the it's going to change the pricing and as well as the requirement and the demand and the market scalability and of course the manpower requirement. It is all on the major four segment. It is on the AI hardware, automotive, and 5G infrastructure, and of course it's going to be a 6G infrastructure and edge computing and IoT. I think I'm sure actually most of the faculties are from electronics background. I'm sure actually that they can understand in every segment. It's almost changing from one it's a yuga to yuga. It is AI yuga to is everything. You talk about VLSA or embedded or communication, everything. It is going to be on AI. Okay, so this. And if you see that current trend market in India and as well as if you see the global, out of global market, if you see that more than 50% is going to be a design will happen in India. And of course, if you see that usable, where we are going to use this concept and technology, yeah, there is 100 to 110 billions. Okay, it's more of industry and government in India itself. Okay, so out of my India market is going to be 10 to 13%, and global share is about 10%. Okay, so almost we are on at par with world requirement. Okay, if you see that global requirement and India, it's almost we are 10% to 13% requirement in India itself. And market comparison, yeah, if you see that global market and India market, overall 45 billion to 105 billion in the same period. Why I am showing this requirement is actually when we are talking about the huge requirement on this particular industry. Okay, see, it is also like how we are channelized and as well as what is the roadmap we have actually for next 5 years. Okay, key takeaways like global market strength. Okay, it is strong growth driven by demand in AI, data centers, automotive, networking, and consumer electronics. And India's rapid expansion, as like the government is also investing on the data centers, and as well as actually like as like your uh, Odisha is also trying to come with a lot of policies in semiconductor industry and as well as the EMS segment, because I was also part of your both the initiatives in Karnataka, because both the initiatives, the documentation is done in Bangalore, and approvals has been taken from IESA. I was also part of IESA. So even thanks to the Odisha government, so is taken good initiative in particularly on policy making of semiconductor. And in policy support, this is what actually the India mission and as well as every state is coming with their own incentive policies. If you take the emerging ecosystem, yeah, domestic requirement and as well as uh, the global requirement. So how much we can consume in India and how much it is outside India. How much we are able to do export from these the policies what we are going to drive. So of course some of the states now already we are talking about the world #1 exporters of mobile phones, and similarly like in other automotive and as well as some of the other communication equipment, we'll be in #2 or 3 in by coming another 3-4 years. Yeah, it is not only we are exporting. It is also we are going to be the maximum consumer of these semiconductor-based electronics equipments. And now we are talking about
Hello.
yes, please one second.
Yes, sir.
Yeah, so yeah, we are talking about moving from 3 nanometers transistor level of Moore's law into the modern reality of power and cost constraint, complexity changes, and system level optimization. Okay, is it are we in the is it in the same academic level also, or is it industry moving and academic is still we are trying to learn or understand actually what are the important parameters we should take care of the syllabus or academic learning. Is it the tool or is it capacity building, or is it we are talking about the faculties, or is it we are talking about only the applications, or we have capstone projects in hand? So that is what actually makes difference in academic also, like moving from transistor level to your complexity changes. See, here we are talking about general purpose chips in earlier days. Now we are talking about application specific system. That means what actually? Like, is it a transfer focused or scaling driven or a holistic design or performance driven? So you are talking about transistor focused chip level, that is the general purpose chips. Now we are talking about holistic design, overall performance driven based chips. That means actually each chip can perform for 2-3 applications. Semiconductor no longer just a smaller transistor; they are integrated system designed for specific applications. Major, if you see the technology pillars, as I mentioned earlier also, like AI-driven custom silicon, advanced packaging. Yeah, this is one more thing we'll address later, the advanced packaging and new materials, and novel architecture, memory-centric computing, and AI-enabled designs. Like AI-driven custom design. Already we are talking about many job opportunities coming reduced actually in VLSI design itself, because many of the work it is already taken over by AI, including packaging, or it can be of routing, or it can be of pin assignments. Many of the level actually it is already reduced. So that is where actually even to whatever the packages or tools are available. I think in future the students also think of AI driven VLSI design. Okay, and also similarly on embedded system also, like can we take care of AI part of the embedded system? So while writing the program, you have to be of machine learning, and in turn, actually, it has to be edge computing also. And when we are talking about packaging, okay, so it is I'll come detail presentation on the packaging. And the material actually we are talking about, instead of talking about silicon only, now we are talking about gallium. Okay, and also there are many other research are happening to use the better material. It is not only to reduce the cost, it is also to take care of the on the temperature, or it can be of the density, or it can be of latency. So they all we have to take care of material science. Okay, and about the architecture, yes, it's the revolution is created. Instead of a single architecture, it is a multiple architecture in the single chips has come. Okay, which will it is also like on the computing quantum computing devices pushing performance boundaries. Okay, and memory centric computing. So one more is actually we need to concentrate on when we are talking about processing in memory, is it we are talking about everything in the memory, or it can be of additional processing very close to memory. So this is what actually we'll go to study about memory-centric computing also. And finally, we are talking about a design of chips using AI, and also using AI for applications. So again, we are talking about custom silicon with AI. We are talking about GPU, NPU, and TPU both. All the three in single chip. So is it viable, or is it are we putting more pressure on the devices? Is it we have enough libraries and fast actually to take care of this? Yes, it is already started by NVIDIA, and in future it is going to be more and more fabs are going to come with additional libraries, and the future engineers is to take care of all these three parameters in one devices. Okay. So all the AI chips are fundamentally different from CPU, optimized to matrix operations rather than the sequential processing. We are talking about chiplet architecture and 3D integration, heterogeneous integration. So modular approach combines the multiple dies, flexibility, and yield improvement. And vertical stacking enable shorter interconnects and high bandwidth. In the sense, most of the devices we are talking about interconnects between the memory and as well as CPU with a long distance earlier. So now we are talking about as much as actually is putting the memories very close to that particular GPU itself, so that we can reduce the time and increase the working. Fundamentally, it will give the better results. Okay, combining different technologies and materials in a single package. This is what actually I was talking about. Is that devices can be sensitive and with inbuilt sensor also. So advanced packaging has become as a critical as transistor scaling, enabling performance improvement through system level integration. I'll come to that part also. Okay, when it comes to memory centric computing, more of bottlenecks was actually on the data movement between the processor and memory consuming power and time. So this is now actually taken care by on 2D and 3D levels of implementation of the devices. Means, earlier actually one level was it is taken care in while designing. Now it has taken care of 2D and 3D levels of devices on a single chips. Okay, and improvements in the bandwidth and as well as energy efficiency. So this is what actually will happen actually on. But while doing all those things, where we are using these devices, that is also important. Are we using it actually for communication, or we are using it for a medical application, or are we using it for defense application? Depends on the application. These devices has to be designed. Otherwise, see, even though we are talking about 3 nano and even might be, sometime after 5 years, it can come to 1 nanometer. But definitely, when it comes to continuous working and for rugged applications, still actually we'll go with the older technology, like, even up to 120 or 150 nanometer, because that gives a more ruggedness in the chip level itself. Okay. Again, we are talking about AI in semiconductor design. Okay. AI optimizes chip level layout and connection paths, reducing the design time and improving performance. Means actually, like, instead of manual routing and as well as something like, you can put your own conditionals, like, I want a performance of this, what is the time and clock, and as well as latency. Then automatically the placement, it will give automatically placement and routing the tool itself, so that you can pick up actually the best one, and you can continue that designs. And automated testing and as well as validation ensures the design integrity and catch errors early. That means, see, usually that devices, even it will take about years actually to design. But if you don't find out the errors, so in the early stage, then we'll end up with a lot of problem in later condition on the production, and as well as wasting our time and money both. So this is one more thing AI can take care of. We can put all the constraints, and you can start designing. So whenever the error occurs or bugs comes, automatically it reduce that errors, and you can keep rectifying the problems. This is one more we found actually AI can take care of verification. So, and also, like, prediction, like, see, we are talking about time limitations and constraints. So we can fix up everything in AI. Like, this is what actually I'm looking at. The outcome, it has to come under this particular ratings. Then you start designing, every stage AI can take care, and as well as it can instruct you actually, like, where you're going wrong. And we're talking about traditional EDA and as well as cloud EDA. This is one more thing, now I think Government of India is also supporting the C2S for academia and as well as startups and MSME, which is of earlier EDA tools was more of your system based, like, the software was getting installed in your system and you are paying for that particular year or something. So now we are talking about cloud computing, cloud EDA license. Okay, and see, it all depends on how much time you use. Okay, you pay only for that particular time, and also, like, you, as much as you use the drives models, so you pay only for that. So this is how actually the cloud it has reduced our the cost of design also. Hope your institutions are also coming under C2S. If not, actually, please apply anytime, whenever it is open. I think now it is open. So C2S, that is the chips to startup, you can apply for it. So your institution will get free of cost this tool, the Cadence, Synopsys, Mentor, any of these tools, and you can be a part of India mission for semiconductor designs. See, we are talking about the chip actually to the final fabrication. It is also fabless. Okay, you can that's what India is most popular for, and in future it is the two levels. One is of course and the FPGA based, and of course on the simulation based. Okay, this is the one more level India can emerge, and your institution also can concentrate on this. So, okay, now coming to the materials. Okay, we are talking about EV and power electronics and RF. So when we're talking about continuous usage of 24/7, 365 days usage of our semiconductor devices for better applications and bigger applications and more frequency, energy. So we need better materials also. Like whatever the present materials is going to get upgraded to the gallium and silicon carbide and as well as emerging gallium oxide. I've gone through some of the website of some of the research areas. I think they are coming with some more 2, 3 materials, other materials also, which can take care of breakdown voltage. Like even it can be of see, we are talking about 24 volts, or it can be of 1.2 volts. So now as much see what we want actually the more power backup. Okay, more usage of the less power consumption and thermal stability and more power efficiency also, like. Okay, these are the things can be taken care by on material science, correct? It is not only your designs. So then you need to come with a lot of other innovations in this particular category. So we are talking about the AI is the first one, and the second one is the material science. Yeah, this is what actually the comparison. Okay, safer. If you see that the higher breakdown voltage, better thermal stability, voltage switching losses, and as well as the smaller sizes. And if you see the application-wise, electrical vehicles, because it goes in inverters, onboard chargers, DC charging system, benefit for improved efficiency and reduced size. And if you see that RF and the 5G, 6G systems, high power RF amplifiers, radar systems, and satellite communications. And faster chargers because smaller, lighter, more efficient adapters and phones and laptop or EV vehicles. So this is the applications if you see at home appliances and as well as industrial appliances and consumer items, and even the EV of outside your system itself. And when it comes to renewable energy, because it works on more of high voltage, and so we need a better semiconductors. In all this, if you see that all the 4 categories are different, okay, and all the 4 categories, devices are different, applications are different, working voltage or current and applications. When we see all the 3 parameters, okay, so we have to take care of the devices as much as possible in designing itself. Okay, when it comes to more of fabrications, as like India is taking care of now coming with 4 or 5 fab in India, like Gujarat and as well as Assam is taken, and also like understood actually like your own state is also coming with some fab, and our AP is coming, and as well as Karnataka is investing on fabrications. See, if you see that overall sustainable semiconductor fabrication units, so we need more of it is energy dependent, and water high like quality water is also required. And when we are taking care of both the things, we need to create the green environment also. Are we taking care of these 3 important sustainable model? So otherwise, even though we come with like fabs, finally we'll end up with a lot of environmental issues. So this is all on when you come up with the concepts and technology. Now we are talking about applications driven. So these devices, when we start designing, are we taking care of applications also? So I told you some of the applications like an EV and like RF and renewable energy. So are we into that? When we are taken the devices designing, are we with applications also? It is not only like what is the capacity and capability we have. It is also like where we are going to use this the devices. If you see the applications, the density, power efficiency, and now we are talking about not the wiring, electrical wiring. We are talking about photonics also. So this is one more research area. I think everybody can think of it. The photonics is going to be a fast performance and as well as bandwidth it will increase. So this is what actually that one slide. Yeah, this is what. Optical interconnects use light instead of electricity, enabling dramatically high speeds with power energy use. See, all these, it is not only the imagination. It is also, might be imagination also. But if you think of in future how the silicon is going to be or semiconductor is going to be with application. So these are all everything, whatever I'm talking about, everything matters. So next is density, because we are not talking about like 1 bit, 2 bit, 8 bit, 10 bit, 32 bit, nothing. So it's more of packing over processing power into smaller pieces to handle massive AI workloads efficiency. That is one density we need to talk about. And it is going to be a global density also. Like, we are going to sit here and somewhere our system or our computing is going to happen somewhere in the other part of the countries. If at all, that is the system, then how to take care of that. Reducing energy consumption per operation as the computational demands skyrocket. In the sense, so like, power efficiency is one more which I'm expecting that, it is not that, we have a sufficient power. It is, we are talking about renewable power energy attached to all these data centers or any of the semiconductor industry working about. So we want a 24/7, 365 days power, uninterrupted power. So we are talking about when uninterrupted power is given, automatically we need power reductions. Like, these components, whatever it is we are using, it has to be on low power consumption. And when we are talking about advanced packaging, okay, that's what actually I was talking about, 3D integration and optical interconnects. It'll give the more of performance and bandwidth. So here we are talking about another three level of high speed. Okay, connectivity. When we are talking about 5G to 6G, we are working on terahertz. Okay, higher frequencies that offer greater bandwidth, but phase propagation and integration handles requiring novel semiconductor solutions. And we are talking about RF and AI convergence and the sensing and communication. Next generation networks merge with data transmission with environmental awareness of the autonomous system. So everything it is on the carbon footprint also. So we are talking about now today any like design at our own lab level, but finally it has to calculate on the global environment conditions and carbon footprint also. So when we start designing, we have to take care of everything. So across all the ecosystem and all the stakeholders. So again, we are talking about applications. One more is automotive applications, EV, ADAS, and autonomy. So these are the things which will expect that every devices or semiconductor devices perform and sophisticated to the best of safety and security of the system. And see, when we sit for the drive, we expect that, hello?
Yes, sir.
I think somebody is scratching
Hello.
on that.
Yes, sir. Yes, sir.
Somebody is
Hello,
scratching
sir.
on the, yeah. Okay. So next level is actually when we are talking about applications. Like one is actually on the data centers, next one is on the communication, third one is the automotive electronics. The next one is, you can see, I'm going to talk about the next level of somebody is scratching that on the screen. So writing on the screen, somebody is writing on the screen.
No, sir, no one is writing.
You can see a yellow mark on the screen.
Yes, sir, there is an yellow mark.
Yeah.
Sir, no, sir, no one is writing.
Okay, I cleared it.
Okay. So now it's not visible.
Yeah. Okay. The first one actually we were talking about the semiconductor design itself. Okay. From the concept level to the technology level. The second one actually, when we start designing, we are talking about the applications, considering application, how to take care of the devices. The third one now, what is available actually, even your institution can start working with the FPGAs. I think you might be already introduced FPGA as a part of the curriculum, but in future the FPGA is going to be SoCs. FPGA is going to be of more of it will take care of your memory and as well as your computing capabilities also. Like one is like that now the major players like Xilinx is taken over by AMD, Altera is taken over by Intel. So that means actually major shift is going to happen in semiconductor industry in terms of FPGAs. Okay, even that is the then a lot of Chinese FPGAs have come with just hardly about 100 rupees to 200 rupees FPGAs have come. So students they can start using these FPGAs for basic applications before getting into the CMOS. Okay, getting into the fab itself, they can start working on these FPGAs. Okay, and if you see the device behavior, architecture, memory, packaging, and design for with all the building logics required, okay, it can perform in every stage. So because we ourselves we started using our FPGAs way back in 2001. So in fact, actually, I was the first person to design a first FPGA board in India with the Xilinx device. Okay, and in fact, these boards I supplied to most of the IITs and NITs that time. And after that, no, we evolved with a lot of FPGAs as and when actually the new devices come. Till now, actually, we designed with Spartan 2, Spartan 3, 7, 6, 7, then RTX, now Zinc, Vertex, almost all the devices. We created the development boards, and using these boards, we created the applications. Okay, and we developed some of the applications for defense and aeronautical applications also. Okay, these FPGAs are versatile and as well as very flexible to use for any of your applications. And almost all the IPs are available. And if not, actually, the students or any of the designers can develop it themselves. And also, like these are the companies are also providing some of the libraries which is most popular. And also, like whatever the upgradations are happening, it's available to the user. We have designed some of the PCI-based applications. Now we started working on some of the microcontrollers on FPGA, like RISC-V we developed. RISC-V we have developed it to the almost about fourth level with lot of accessories, even including your memory interfaces, or it can be of HDMI interfaces, or it can be of your VGA. Uh, Almost all the communications protocol also we developed in that. Okay, so using the FPGA, I think you can do a lot of miracles before getting into the real fabrication of devices. So even though like you will be definitely, many of the faculties are working on latest technology and latest VLSI designs. But before that, you can also try with the FPGAs, and then you can move on to designs, so that you will never fail on conceptually, and if at all you're going for a fab. So industry requirement, if you see that it is more of it's a time bound, and application is specific, and software and hardware both are the cost, and manpower is a huge cost, infrastructure is a cost, and almost we talk about pricing on every stage. At that time, you can try with FPGA, and then you can move on to industrial requirement. So this is what actually we also adopted, because we have already many blocks of DSP and RISC-V, our own built-in, in-house developed, and the same thing, we also working with some of the clients on using the same. So if you see that FPGA in academic curriculum, okay, yeah, starting from algorithm to architecture to RTL and the software interface and performance. If you see every level, FPGA can perform better. Okay, and because we are getting algorithms, and as well as while doing architecture, like we have optimized the designs already available. Okay, same thing, we can adopt it. Okay, so this is how actually this moves. So in future, it is going to be an engineer's tool. See, might be, your academic level, still you're not taken seriously about FPGA, even though just, it is a part of your curriculum in the 4th semester to do some full adder and half adder, but you can do beyond that. Okay, and if at all, you require any of some of the capstone projects, let us know. Actually, we are ready to support your student, because the industry needs a lot of FPGA engineers. And but students are after 3rd or 4th semester, they'll forget about FPGA and they'll get into the CMOS. So ASIC design. So if they are good in basics of Verilog and fundamentals, and they are good for industry, we need a lot of engineers, but skilled. Okay, so that skilling now industry is also not able to give it. So I feel you can build that in institution level itself, and industry can directly take care of on onboarding. So this idea of FPGA can bridge all the 5 applications, like bridges, devices, architecture, memory, software, and applications. And so while doing designing also, like you can think of whichever the devices externally attached to the FPGAs. FPGAs are not constrained about is it I'm talking about 5-volt devices, or is it 12 volts? Now we are talking about 4.5 volts, 3.3, 2.5, and now 1.2 volts. So that is what actually your mobile devices needs, like low voltage and high performance, low voltage and maximum power utilization, so that I can use my mobile actually for 24 hours. Okay, so this is what actually the power backup is also required. So modern chips integrates multiple functions into single application optimized system. So earlier we improved chips mainly by shrinking transistor. Today we improve chips by integrating computing and memory, communication, and power into single system designed for specific applications. So this is what is going to be future. So I request institution also can conduct some of the like ideathons, which only for semiconductor, what students can think of, it can be of change. So that because we'll be thinking, industry will be thinking on one direction, like this is where actually I can work. Depends on the all the constraints on the financial things, majorly on finance. But students can think of beyond all those things. Correct? It is only on the imagination. So what we need actually for innovation, only imagination. The grassroots innovations required. That innovation later actually can be evolved into the real-time applications or real-time usage that we can think of later. But initially, the students from first year to the third year itself, not about fourth year, the third year itself, they should think of using these like what are the things and what are the modification we can think on now. Semiconductor industry. So one is on the fundamentals and concept, but the second one actually of applications. Like many controllers have come. Okay, many of the devices have come. So think of something using instead of only Arduino and Raspberry Pi. Okay, think of something new devices. See, that can be used only for initial learning of your Python or C. But later, when you adopt the language control, then you can think of something different latest devices. See, earlier we used to have books for like data sheets. Okay, now everything is available on the net. Students can get into the data sheets and think of latest device, whatever it is coming. Think of 8-bit devices also. Still, you know that 8-bit is used actually for your election voting mission. Okay, there are 14 devices are there in one device. Okay, we're talking about breaking or where we can voting missions can be hampered or tampered, but no, it cannot be. It is already many of the hackathons has been conducted in Bangalore also, only to break that type of machines operation, but it has been never succeeded. That means actually the uh, innovators or designers have taken care of such cyber attacks, or it can be of hampering these missions. One second. Okay. Just I take one slide, one more last slide. So this is manufacturing value chain. I think you're all aware of it. Like we talk about IPs, and we are talking about the tools, and we are talking about different equipments for manufacturing, and also some of the custom measuring equipment, the raw materials, the fabric designs, and foundries. Okay. If you see everything, even a small change in one of the concept and technology, when what I'm talking about, so every stage, we need to take care of. So it is, if it is only the voltage, then we have to take care of the equipments also. We have to talk about AI implementation, then we have to talk about the starting from your debugging tools, or the new devices has to come, the new devices has to be applied for the application, the foundries libraries or device libraries has to change. So that means not even the single change somewhere in the concept and technology, everything we have to take care and whole ecosystem of manufacturing chain. So that's how actually the whole semiconductor industry works. And if at all you have any questions, please you can ask me. If at all I can able to answer it, I'll try to answer it.
Thank you, sir.
Thank
Dear
you.
participants, do you have any questions, please?
So even though students may or participants may think actually that these are the things I'm talking about on the imagination. There are something recently we had a conclave, semiconductor conclave conducted in Bangalore, and many of the industries, advanced tool users and developers, they participated. And while doing many of the discussions, this is what actually the points came out. So I'm sure in future academics also can move towards that. Okay. AI, it is not only for your other IT, AI for semiconductor industry also, and also applications. So think of these two in your by conducting some hackathons and ideathons in your institution, so that the students will come with more ideas on that.
Sure, sir. In participants, do you have any questions, sir, for sir?
See, AI is, again, I'll tell you some of the meantime, I'll let them think of some questions. And meantime, they'll give you AI and machine learning are now used to optimize the chip layouts, power,
Sure, sir.
performance, and area, speed up verification and catch bugs early, and predict yields issue before manufacturing, and improve process control in fabs. So this is the 4 levels where AI can give better inputs.
Okay.
And the second one is actually like entering photonics into the devices, so that much higher bandwidth will come, and low power will come, and less heat will be generated by the devices. This is the 3 points, which our optical can take care. That's what photonics we are talking about. So that these data centers, which is continuously working on 365 days, so we need that type of latest devices.
Yes, sir. Participants, any questions, please? Any questions, per
Yes.
sir? Please ask.
Okay, if there is no question, then we can stop.
Okay, okay. Sir, Uday Suryan is asking, what will be the impact of AI in semiconductor technology?
That's what I was telling you. So mainly AI will come into the picture of while designing the device itself. Okay, now the tools also, that's the reason the tools are also getting modified. In fact, 𝗕𝗏&𝗛 is working seriously on changing the tools itself. So the existing tool will not be sufficient actually to implement AI into the devices. Okay, now what we are talking about, AI for chip layouts, speed verification, improvement of process control, and process control in the fab itself. Okay, so that the devices, it was taking at least around 18 to 19 steps actually for manufacturing. In future, it will reduce to even 5 or 6 steps, and predict see, usually once the device goes for production or a fab, if anything a small error or a failure, so whole lot of devices was getting scrapped. So now, before getting into that level itself, so the designing level itself, we will take care of putting all the restriction and conditions while designing itself. So put all the conditions and test your design in every stage. So AI can predict, where the problems may come.
Okay. Okay, sir. Thank you, sir. Any other questions, please? Okay. Thank you so much, sir, for such a wonderful session. And we both, Dr. Kithis and myself, thank you again on behalf of all the participants for your valuable contribution. And we truly appreciate the time and effort you have shared with us today. Thank you so much, sir.
Thank you. Thank you.
Now participant can leave.
Thank you.
Thank you, sir.
Participant can leave.
So here we are, so here we are concluding the day 4 of FSFM 2025. So tomorrow, please join by 6 p.m. Thank you so much and good night.